All right, guys. So we talked about this tunnel or the quadrupole, and we said that this tunnel allows the positive fragments to come down through the center and out the other end. So I'm going to kind of draw the tunnel down here, and here's the end, and we get our little fragment pieces that come out of the other side. And this eventually gets into the point of the detector. The detector is going to see these positive fragments, and it's going to have to analyze them, which basically means provide you the mass on them, right? Because this is a mass spectrometer. We can't ever forget that. So we need to be analyzing things for their masses or their formula weights. Well, there's one more thing that has to happen at the end of this tunnel before it can do its job. So what you have to imagine is a little car zooming down the highway. And let's say that this car, after it zooms down the highway, it actually sees a road that curves. Okay, well, what's going to happen is that if this is kind of the size of a little Volkswagen Bug or Beetle, you're going to see it zoom down through this highway as fast as it can go, and then it sees this curve at the end that it didn't see coming until it got right upon it. Well, that's going to be very easy to maneuver, right? It's a little car. It's not going to take much of force to kind of steer that off in the right direction, and away it goes. Phew! You like my sound effects? It goes around the curve without a problem. So nothing really held it up. It didn't have to slow down. It took the curve very well. No big issue there. All right, well, let's say that instead of a little Volkswagen Beetle, I had some type of semi-truck. The semi-truck is much bigger. This semi-truck is zooming down the highway at the same speed that little Beetle's going. And then at the end of this highway, that semi-truck realizes, oh crap, there's a curve. And that truck driver is going to have to turn the curve. Well, here's the problem. We don't control the speed. So that means if these guys are going 70 miles an hour down the highway, they have to continue to go 70 miles an hour. They cannot slow down. They cannot push a brake. So it's going to take a little bit more effort for this large semi-truck to turn this curve, right? So as it approaches this curvature, it's going to take a little bit more effort to get it to curve and turn around that bend. Okay, so what I've done here is that I've kind of had to make this road a little bit wider in order for that to happen. So what you're seeing is that this curvature path is going to be very important, because as these molecules curve around this bend, they're going to hit at different locations up here when they cut around that corner. And the location of where they hit is going to be associated with the formula weight. That's how the detector and what we would call the collector plate does its job. It figures out the location at which it's getting a signal, and that location is assigned a formula weight value. We know that if this is a semi-truck that weighs 69 formula weight, as it races down this highway and turns the curve, this spot is where the 69 will hit every single time. If it's a 69 molecule that just lost an electron, that's where it's going to hit. If it's a 69 fragment that's part of a compound that also lost an electron, it's 69, that is where it's going to hit. The little Volkswagen Beetle, maybe this is a 29 formula weight. It zooms down the tunnel, turns the curve, and it hits at that spot on the collector plate. Well, because of where it hit, because of that location, the collector plate understands that that spot is where a fragment or a molecule that weighs 29 That's where it's going to hit every single time. All right, now keep in mind, isotopes are still present. So if we do have a fragment at 29, well, we probably have a fat little carbon or a fat little hydrogen, and we would see maybe 30s come along as well. We could also maybe see some 28s come along in that position. If we have a 69 fragment, well, we could also probably see a 70 fragment, or we could see a 68 fragment, or we could see a 71 fragment. I mean, it just depends on how many fat little pieces are there. So if a 69 hits, then a 70 and a 71 and a 68 will also hit around in that cluster. But the MS, it can distinguish those differences without a problem. All right, now let's take a look at a better diagram, maybe, that we're going to see right here. And this is representation of the curve at the end of the tunnel. All right, so my molecule is going to come in through this entrance. So there's the ionizing filament right in here, all right? And we're getting some gas flow. Some gas flow is coming from the instrument because we've got to keep this thing pumping full of gas. Typically, this gas flow is going to be helium. So the helium is getting mixed into that chamber with my compounds, and then this molecule is going to go through an electron beam. So the ionizing filament. I'm sorry, let me go back. It's not coming in from that direction in this diagram. It's coming in with the gas flow, right in here. So this piece is my ionizing filament, and that means that's where my electron beam is coming from. So this is where the molecule gets slammed. Maybe toothless. Well, when that positive charge happens inside of this little space, we also see what we call an ion repeller. The ion repeller, well, it's going to be a positive charge. And the reason is because when these positive pieces get created, we don't want them to stay around in this area. And we've talked about this before. So this area has to have a repeller. So it has to be able to push my positive pieces through. And that is why that's present. The electron trap. The electron trap is typically for the electron beam. And that electron beam, that's where it's going to be headed. The electron trap can also, though, go ahead and capture some of those free electrons that get created. So it can help kind of do preliminary cleanup. The ion accelerator plates. Well, these are also positively charged. These ion accelerator plates will push this positive piece through the quadrupole even better than the ion repeller that's down here at the bottom. The beam focusing plate, well, that just allows everything to escape out of the ionization chamber at one location. All right, so here is kind of where my quadrupole would be. So this is the tunnel that everything is getting zoomed down through. And then out the other end, we have our positive fragments that begin to escape. So this will do some cleanup. It helps get rid of those negative fragments and maybe some of those electrons that are still behind. Sucks them all out. They never make it to the end. But right here's the curve. And this curve is what helps the mass spectrometer do its job. Notice that it says that this curve is a positive ion beam. All right, well, that's because that these positive pieces are coming through. And this has to be positive. That way it can help push that car and help it turn the curve. Otherwise, what would happen is that these positive pieces would just go straight through. We don't want that to happen. We want them to turn the curve. So because of that, we load this plate with a positive charge, and that keeps it pushed away, right? Positive and positive, they repel each other. Again, I told you there's magnets everywhere. And as it turns the curve, you will begin to see different paths that this thing will take, depending on the weight of the fragment. The larger weights take a little bit longer pathway around the bend and hit at the detector. The smaller fragments don't take as much effort. They can turn that curve a little bit better than the bigger ones. Remember, the beetle versus the rig. And they will turn the curve a little bit better and hit at a different spot. And notice here is mass 44 and 45 and 46. So over here would be my collector plates. And the collector plates are called the Faraday collectors. That's just a fancy word that comes along with them. And it will measure, oh, we got a signal, we got a signal, we have a signal here. And what begins to happen is that it begins to generate a mass spectrum for you. So it says, well, we've got a positive, we have a positive, we have a positive. Oh, we go back, we saw a little bit more, we saw some more, we saw some more here, we saw some more there. And it begins to gradually generate this mass spectrum for you over a course of time. And we begin to get these series of lines. Again, the height of the line is very important because the taller the line, the more abundant that fragment is. I'm seeing it more and more often. That's kind of the common thing that's escaping the quadrupole, coming around the curve and hitting the collector plate. That is what the most common fragment is when this thing gets slammed with the electron ionization energy. All right, so there's one diagram. Here's another diagram. It comes from an old organic book that we used to use. It was a Paula Bruce textbook. And it basically tells us the same thing, just in nice, pretty pictures in color. So here is my sample, and these are neutral molecules that begin to come in to the ionization chamber, and it goes through what we would call the electron ionization beam. So that's what these little red lines are here. All right. Notice we have the option to turn this guy on or off, and that is what we would call the filament. So when we run the instrument, we want to make sure that this filament is on or off. If we want to measure things, it has to be on. That means the electron beam is on. If we don't want to measure things and we're not ready for that yet, we can turn that off. And the reason is because this thing has a lifespan. That filament will go out over a course of time and it has to be replaced, and it's not cheap. So you really only want to use the filament when you absolutely have to. It expands the lifespan. So the electron beam gets slammed or slams the particle. And then what we end up seeing is a positive piece that gets created in the mass spectrum or spectrometer. All right, so these things zoom down through the tunnel. Notice it says 2 vacuum pump. Whoop, goes out. All neutral molecules, neutral fragments, and negative ions get pumped out of the system. This is kind of where the quadrupole would be, or a part of it. My fragments come down through. They go through this curvature, and they begin to separate out into individual lanes. This is where the separation begins to take place. They come out the other end, and they hit on the collector plate that's down here at the very end. All right, so there's kind of the overall schematic of a mass spectrometer. And when I show you this, I'm doing it because you're probably going to have a test question at some point in time that will say, draw the schematic. Well, you can be this detailed if you want, or you can be simple. And I like simple. So if I ask you to draw the MS schematic, then as long as you do this, you're going to get by with a correct answer. We don't need to really all the details that go into the inside of it. I just want to know, do you really understand what is present and what things are doing? Yes or no? So you need a sample, and the sample needs to go into the ion source, and this creates the charge. And these charges are typically positive. They go into the mass analyzer, which is part of the quadrupole, as well as the bend. Those positive pieces will escape, and the detector will see and measure the formula weights of those pieces as they hit. All due to location, location, location. If you've never owned real estate, you will one day, and you will know the term that I just used and the importance of it. And then finally, that detector gives a signal, and that signal gives us some data analysis, and this is what generates our mass spectrum and relays the signal to the computer system. All right, now before I stop this video, I just kind of want to review some topics here. At least one. And here's a question. And it says, which of the following fragments produced in a mass spectrometer would be accelerated through the analyzer tube? So this is a type of question that you might see on a test. And if we take a look at this question, it's giving me all of these kind of pieces of a molecule or fragments. Who knows where they come from? It doesn't really matter. But I want to know which one of these fragments would be accelerated. Well, some of these are going to be very easy. So if I take a look at this first one, this one has no positive charge on it, right? It's got this dot. That dot represents an electron. That electron is negative, but that's it. So this will definitely not go through the mass spectrometer. It's just not going to happen. All right, and then I take a look at the second one. This second one's going to be pretty easy too, because look, I see a full-blown positive right there. That full-blown positive means ding, ding, ding. It's going to go through the quadrupole, and it's going to hit the detector at the other end. That's an easy one. The third one, let's hold off on that just for a second. The reason is because I see a positive and a cation, or a radical. The fourth one we can probably go ahead and talk about. The fourth one, it looks like there is a double bond. And this double bond would be a negative source, right? But it's a bond. It's not really a charge. But that's a negative area of the molecule. It is not a full-blown negative charge. So we really can't look at those areas to help make our decision. What I see here is a radical that's one electron that is going to cause a negative charge. And we know that unless these things have positive charges, they're never going to see the daylight. So that one's get crossed out. Well, we take that reasoning to the very last one. That very last one, yeah, this is a negative bond. But you know what? That's no big deal. That's not really a full-blown negative charge right there. That is a negative area of the molecule. But we do not see a dot that's listed, a full-blown negative that's going to be there on that molecule. I do, however, see a full-blown positive. Ding, ding, ding. That will go through. It will reach the other end of the detector. And you've got to keep in mind, these things are fragments of a molecule. This fragment could have functional groups on them. Without a problem, they will have functional groups. No big deal. As long as it doesn't have that one little negative, that one little electron, that's what's going to cause the problem. Now, we're going to go back to this third one. This third one, well, I see the positive. It's right there. But right beside of that, I also see a dot. And that dot is, of course, an electron. If that dot was the only one that's there, then that thing is going to be a radical, and it will be removed. But the problem is that I also see the positive that's right beside of that, almost on the same carbon. So the question is, does that really go through or not? So some of you might be prone to say, well, the positive will cancel out the negative, and that becomes neutral, and the neutral molecules don't really go through the quadrupole. And if you go through that reasoning, wrong. It's easier than that, people. As long as it carries that positive charge, and it does, then this ding, ding, ding will go through the mass spectrometer. All right? So again, it doesn't matter what is present. It could have one electron. It could have a double bond. It could have an entire OH group. And think about it. The OH has 2 pairs of electrons on it. The functional groups are going to be okay. As long as it has a positive charge where it fragmented, if it carries that positive charge, it will go through the other end of the tunnel and it will see the detector. All right? So don't let those questions throw you off. Simply look for positive charges. And as long as you do, you're going to get the correct answers because that's all that you need to be looking for in these scenarios. All right, so that's where I'm going to stop. We'll come back. We'll talk more about MS theory. We're pretty much almost done with the instrumentation part. Not really too much that we need to talk about after this. And we'll go and we'll start interpreting MS data.